Syzygy, episode 37, Crazy Donut Moon Theory. And welcome back to another edition of the Syzygy podcast. My name's Chris Stewart. Sitting opposite me at the table once again is Emily Brunston. Hi, Emily.
Hello, hello.
So this week we're going to be talking about the moon and where it comes from. Now, this is one of those episodes where, I don't know, naively you'd kind of think this one's going to be an easy one. Right, it's the moon. It's the closest thing to us in space. It's just up there. It feels like you can just reach out and grab it. It's actually further away than you think when you look at the scale diagrams of it. But
yeah, it turns out the moon's quite far away.
It is quite a long way. And in this 50th anniversary of actually landing on the moon, it's worth going back and just reminding yourself, yeah, it is actually a really long way away. But anyway, it is our closest. And it kind of feels like that one's, that's the low-hanging fruit in the astronomical orchard. To just torture that metaphor a bit further.
We need to stop now.
All I'm saying is that one should be the easy one. And it turns out not so easy when you look into the details of where this big chunk of grey rock that dominates the night sky actually came from. So we will be unpacking all of that shortly. But before we do, Emily, there's been a little bit of news on a satellite which has gone up to shoot things at asteroids. We talked about this a little while ago. What's going on?
Well, Hayabusa has managed to send its big bazooka boof into...
Sorry, it's what?
It's...
I mean, it had a few different...
I can't remember what the thing's called now.
I can't remember either.
It had what was it like? They had the little rovers that was called like A and B, right?
Yeah, that's right. That's right. That was the episode where we did have a few issues. I had a few issues about the Japanese Space Agency's naming procedure. I haven't heard back from them.
No?
Strangely, no. But this is the Japanese satellite, Japanese spacecraft, which has gone to an asteroid and is shooting it.
Yes.
Shooting it with different sized weapons. And remind me why we're doing this, other than it just, it sounds cool if dangerous and a little bit sort of, I don't know, violent. Why are we doing this?
So this is a sample return mission.
Right, that's right. It's going to be bringing it back.
Yes. And
So
we wanted to get stuff from not just the very top of the surface, but also from a little bit deeper down.
Right. And without actually landing on the surface and drilling down in, which is a difficult thing to do on something with very small amounts of gravity, because you tend to just bounce off. What you've got to do is blast it with something and then kind of stick out a big baseball glove and vacuum some of the dust that comes off.
Oh, your metaphors are all over the place, Chris.
Look,
baseball
I'm sorry,
gloves and
everyone.
vacuuming.
I'm sorry, everyone. I'm working on it. Point is, it shoots the surface, and then stuff that gets blown up off the surface and from underneath the surface, it then hoovers up, collects, and is going to bring back home, which is cool. So when we reported on it a couple of episodes ago, the Hayabusa had just shot a small pellet at the surface and gone and knocked up a bit of dust and collected some of that. But it also had a big bazooka-y thing, which was like, the bigger part of its arsenal, just waiting, okay, we're going to fire this one down. And that was to get under the surface. And it's done that now. And we know it's done that because they've sent back pictures of it going, there, that big cratery bit, that new hole in the surface, that was ours. We did that. Yeah. So, I mean, it is violent, but it's violent for a reason. We're going to learn lots about composition of asteroids, where this stuff comes from.
Yeah, solar system formation.
Yeah, which is all very exciting. And the only way that you can really learn about that is to actually take bits of it and bring it back home to study in depth in the laboratory, which is what they're doing. So that's kind of cool.
Very cool.
Well done, Hayabusa, and your intriguingly named little sidekicks up there on the asteroid. Anyway, that's the end of that news. Time to move on to the main event, which is the moon. We are going back to, 50 years since we first stepped on the moon. So it is a big year for that. There's going to be lots and lots and lots of looking at that over the next couple of months all around the world. NASA's going to be going absolutely berserk with this sort of 50-year anniversary of footprints on the moon. And, rightly so. So it does kind of beg the question, what is this thing that they stood on 50 years ago? How much do we know about it? And like I said at the top of the show, surely this is the easy one. Astronomers ought to have worked that one out long ago. But Emily, I have a sense that you're about to tell me that life isn't always so simple.
Well, yes. So we've got a bit of a list up here on my whiteboard, which is kind of
do.
the ideas that we park when we think, oh, that would be great to talk about in a bit more depth, but we just don't have time right now. So we'll put it up on the board and we'll come back to that and do a proper episode on it.
Yeah, and I don't remember Where Did the Moon Come From went up on the board, but it was a while ago.
It's one of the very early ones. Yeah.
Yeah, we should get to that.
Yeah.
We said at the time, like, yeah, that's an easy episode. Just sort of whip that one out, and then Emily goes and does a bit of homework on it.
Yeah. So I thought this morning, well, okay, I'm going to do my preparation work. I'm going to.
You mean a couple of weeks ago when you started the research?
Yeah.
Not
sure.
just this morning.
Yeah. I'll knock this out and
Easy.
in a few
Easy
minutes
one.
it'll be fine. And then I got reading, and my word, it is fascinating because we've got a puzzle with the moon.
Okay.
I mean, you think of something so mundane that you see literally all the time in the night sky that's so big, would be something that, okay, well, that came from this place. And, we know where the Earth came from, pretty much. So why wouldn't we know where the moon came from?
Sure, I mean, makes sense. Surely it's always been there and it was formed at the same time as the Earth and, mission accomplished. We know the answer to that one. No?
Well, as in so many other cases in science, you think, well, okay, we'll just do this little test. It'll just confirm the theories that we have. We'll all be done and dusted. We can go down to the pub.
Piece of cake, because we already know the answer. We just have to confirm it.
Yeah, this is not one of those cases. This is one of those cases where it turns out you do your piece of testing and it just turns up 100,000 more questions that you didn't know you didn't
Go
need.
figure that the universe is more complicated than we thought it was. Yeah. Who'd have thought?
Who'd have thought?
Because that never happens.
So it's fascinating. And some of this research is very recent. So I'm looking at papers from 2017, 2018 as well. So
Right.
really,
Okay, so this is really recent.
cool stuff.
Okay.
Yeah.
So the extent of my knowledge about the moon pretty much begins and ends with, wasn't there like some enormous impact a long time ago that knocked off a huge chunk of the Earth and whatever hit it, and that kind of formed the moon? Is that vaguely right?
Our basic formation
Okay.
theory.
All right.
Right. So we'll start with there. So
Okay.
we think that a Mars-sized body struck the Earth very early on in the solar system.
Okay, now just on step one, a Mars-sized body. That's not trivial.
No.
That's not a sort of, what was that? That's a planet hitting another planet. That's a big impact. You'd notice that in a big way. Fortunately, there wouldn't have been anyone around at the time to notice that. We're talking a very long time ago.
Very long time ago, yes. And then, so the rough plan, sort of the rough theory goes that this object hit, it was maybe a bit of a glancing blow, threw up lots of material from both planets.
It would, yeah.
And that material sort of flew into space. Most of it coalesced into a ring around the then sort of very hot, molten, rocky Earth. And eventually...
So for a while there would have been really hot, volcanic, crazy Earth with rings around it.
Well, maybe not plural. It's a sort of a
ring.
debris disk,
Okay.
maybe.
So not
more,
sort of
is a better-
Saturn-like, more rubble.
Yeah. And maybe something like 1/10 of the current distance of the moon. So a lot closer as well. And then that sort of stuff just got to kind of coalesce, smaller things hit other things and stuck together. They're quite sticky if they're molten rock, apparently.
Yeah.
So,
Again, go figure.
Yep. So you stick together more and more and more until you get the moon, which is there.
Okay. So that seems reasonable theory-wise. That seems plausible. I'd believe that if you told me that was the truth. Does not know?
Well, there's arguments for and there's arguments against.
So this one's
theory.
not settled. Okay.
It's not settled. And in fact, there's quite a big kind of sidetrack argument that we need to maybe incorporate as well. But I think maybe a good place to start would be to think about when in our solar system's history this whole story happened.
Okay.
Because it wasn't kind of, 4:30 last week on a Tuesday, right?
We wouldn't notice that. Yeah.
No.
But what you're saying is that this is part of a bigger picture.
Yes.
The solar system
Yeah.
was doing all sorts of whacked out stuff anyway, so we need to put the moon into that context.
Yeah, the solar system did look like a very different place than it does today.
Okay.
So we did a whole episode on where does the solar system
We did,
come from.
episode 23, if
are.
my and your memory is correct.
The number that I just told you
That's the
minutes
one.
ago is true.
Yeah, I knew it. I mean, I do have all of the episodes committed to memory.
Yeah. So our solar system formed at the same time as our sun, right? And so this is all happening from about 4.6 billion years ago. So quite a few old years ago.
Yeah, long time.
If we call 4.6 billion years ago kind of t equals 0.
All right, that's when we begin this story.
Then it might be easier to sort of think about this in terms of timescales, right? So at 0, we have basically a big gas cloud, gas and dust. It's got lots of sort of stuff just kicking around. Maybe looks a little bit like some of the nebula that we see from things like Hubble. Maybe something as big as the Orion Nebula was where we came from. And then maybe, we don't really know this, but it's a possibility, maybe there was something called the primal supernova.
Ooh. Okay, haven't heard that one
exciting.
before. What's a primal supernova?
It just means there was a star that reached the end of its life, had made a huge explosion, and the shockwave from that explosion pushed together some of the gas and dust in our cloud of stuff that we're
So this
in.
isn't supernova of the star, which then became the sun. This is somewhere else. This
Nope.
is another star elsewhere, but not too far away, close enough that it would send a shockwave through our cloud of gas to go, hey, start collapsing down and doing
Yeah.
stuff.
And that just pushed everything a little bit closer together and basically triggered runaway collapse. So we don't know exactly if that was the case, but, it's a reasonably likely scenario.
Okay, seems plausible.
So that's time equals 0. So from about 100,000 years after that, then we have got something called the pre-solar nebula. So it's this collapsing cloud, collapsing cloud, collapsing cloud. And then the sun started to form. And it formed as a protostar, so pre-sort of star. It was a nasty old thing, well, young thing at that point.
Yeah, because I remember you saying in the past that baby stars are not sort of calm and relaxed and kicking around, going goo on the carpet. They're really quite violent things, quite nasty.
Really,
things.
really nasty places to be around. So they're still accreting matter, so they're taking on matter from elsewhere. They've got jets, they've got strange magnetic fields, they're blasting away winds. It's just, really nasty place. So it's the sun was doing all this at the same time. It had a disk around it, which was kind of the leftover material from what didn't make it into the sun. And that protoplanetary disk, as it's called, is kind of the formation site for all the planets in our solar system. So in that period of time, from when the sun sort of started to form, up until maybe 10 million years after t equals 0, then we've got these processes happening. At about 10 million years, you've got the outer planets forming. And then maybe by about 100 million years, then you've got the terrestrial planets, so the inner rocky planets forming. So all this is kind of just sort of merrily tracking along. Now, it's at this point that what we're talking about, which is interesting, starts to happen. Because the terrestrial planets are not formed in the sense of you don't just have the 4 rocky planets and then nothing else. There's a lot of stuff kicking around in the inner solar system still.
Okay.
So we're coalescing all that little stuff. So we start with particles that are very, very tiny. They start sticking together. They stick together through static forces. They stick together through gravitational forces. And they grow and grow and grow and grow and grow. But it wasn't just 4 things that ended up growing. There were hundreds of these pre-sized planets. And some of them got kicked out of the solar system by gravitational interactions. Some of them stuck together to become the 4 planets that we have today. And at least one of them smashed straight into the Earth.
So in that very early solar system, it was basically a fight for survival. There were lots of things flinging around. Some of them just got flung off. Some of them bashed into each other. What we see now is what survived from that early melee of planets interacting with each other on a much bigger scale than we see now.
Yeah, and we think this is all around the time when the whole solar system was 100 million years old.
Okay.
Now, just contrast that with a term you might have heard before, which is called the late heavy bombardment.
I haven't, but I'll take your word for it.
So, well, goodness me, you've not been reading the right newspapers, Chris. So this is a period much later in the solar system's history where things got flung in from the outer solar system, particularly by the movements of Jupiter, Saturn, Neptune. A lot of material got kicked in, but that was much, much smaller stuff. And that is what caused a lot of the craters that we can see on, say, Mercury, even the moon. So the moon was already around by this point.
Right. So that's significant impacts, but not sort of on the Mars bashing into Earth scale.
No.
There's a big step up.
No, so you sort of hear the word bombardment, you think, oh, well, that must have been sort of around the right time. But
Yeah, that's nothing.
that was
compared to what
500 or 600 million years. So we're talking about much, much earlier
Okay.
and much, much bigger
Yeah.
object.
Yeah.
So it turns out that this object that smashed into the Earth has a name.
Okay.
Do you know its name?
Did we talk about this? Did this come up in
We've
episode
probably
23?
mentioned it.
I think we did, but I don't. It might surprise you to know that I don't remember.
You're not going to pass this exam if you keep going on like this.
I'm not going to pass the exam anyway, Emily. So why don't we just admit that?
Okay, so this object, this Mars-sized pre-planet, if you like, was called Theia.
That's right. I remember now. Yes.
Yeah.
Now that you've told me.
So Theia was very nicely chosen as the name for this object because she was the mother of the moon goddess in Greek mythology.
It's almost like the Greeks knew.
Yeah.
Well, no, wait, it's the other way around, isn't it? Okay, that makes sense. Wow. Okay, so give it a name. So that it's pretty much then settled that that's what happened. That's the best guess.
Well, let's run through our evidence
Okay.
that we have to suggest that this is what happened.
Why
This is
do we
where the
think
moon
this
came
is the
from.
case?
Okay, so the first one is the Earth is tilted over, right? We are tilted over by 23.5 degrees, and this is what gives us our seasons.
Yes. Yeah. Now, as we have discussed before, the large majority of stuff, the planets and things in the solar system, are all going around in pretty much the same plane and spinning in the right kind of way, that they all would have come from the same original rotating dust cloud, and that's how these things work. But because the Earth's tilted by, what did you say it was?
23.5.
Which is quite a lot. That's quite a few degrees, right? It really is tilted over, enough to make a significant difference between summer and winter. That's evidence that we must have been bashed by something. That kind of tilt probably comes from being smacked.
It's definitely a contributing factor, right?
Yep.
Yeah. So it could have been this event that knocked it over, and that provides that explanation quite nicely. So that's one tick.
Okay.
Next tick. Well, turns out when we started to visit the moon and we started having samples and bringing samples back, particularly with the astronauts of the Apollo program.
Yeah, they brought back all sorts of rocks and things, didn't they?
Yeah, tons of the stuff. Well, I think quite a lot. It's hundreds of kilos anyway. So they looked at things like, well, how different is the rock on the moon to the rock on the Earth?
Again, another topic that we've covered before. If you look at the composition, the chemical composition, but also the isotope composition, the different kinds and ratios of elements in stuff that you find out there and stuff you find down here, you can figure out whether or not those two different kinds of stuff are from the same origin. Is the water on Earth the same as the water out there on asteroids? That kind of thing.
Yeah.
Yeah.
So it turns out that particularly for oxygen and for titanium, we're pretty much exactly the same in terms of isotope ratios.
Which suggests
we're part of the same stuff, right?
Okay.
Yeah.
So that's reasonably
kind of
compelling.
Yeah. It means that in terms of solar system formation theory, the moon didn't form in a completely different part of the solar system. Otherwise, it would have quite different isotope ratios of those two different elements.
So it's not a big lump of rock that we then captured. It's coming perhaps from the same place.
From the same place, yeah. Okay, here's the next one.
Yep.
So the moon has a really undersized iron core.
Right.
Conversely, the Earth is a very oversized iron core. The Earth is the densest planet in the solar system.
Is it?
Yeah.
There you are. Well done, Earth, I guess, if that's a good thing. But why would that be the case?
So this works with the theory of Theia in the sense that Theia may have hit with a glancing blow, but then the iron that was in the core of Theia kind of sank into the core of the Earth. And it was really the outer material that then drifted into this ring, got accreted and made the moon.
So the really dense, heavy core, at least some of that, if not all of it, merged with the original Earth's core and made this very large, supersized core, which is way too big for a planet of Earth size. There you go.
Yeah.
But the moon has not enough core, so that's maybe some of the core from Theia that was left over.
Yeah, probably from Theia, I
Right.
would say the iron stuff there. Okay, so that
Okay, so
kinda
more
works.
evidence. That
Yeah.
works. It's all kind of fitting together like a big jigsaw puzzle.
We know that the moon was once quite molten. We can tell from the way that the rock has formed that it must have been liquid at some point and then become a solid again. So it's been melted in the past.
Which sounds like the product of a planet bashing into another planet.
Yeah.
Okay, tick, another puzzle piece.
Yeah, and so all these things put together sort of gives us a reasonable picture of what might happen. In fact, there's some fantastic animations of this, Theia might have looked like smashing into the Earth.
Oh, yeah. We'll find a few of them and whack them in the show notes because that's always good.
Yeah. But
No?
there's some things that don't quite work out as well.
It was far too easy. Okay, what is it?
So one of them is the difference in volatile elements between the moon and the Earth.
All right, what's a volatile element?
So volatile elements basically doesn't want to be what it is currently. So if you think of something that easily becomes a gas.
Okay.
So lots of types of alcohol, for example, ethanols and things, you basically take them out. They're liquids and they become gas very, very easily.
Very fumey things.
Yeah.
Yeah.
So these volatiles are not really found much on the moon, but we have quite a few on Earth. You would have thought that if there was something as huge and catastrophic as this event, which was a global remelting, reforming potentially of the Earth, then those volatiles should be gone from the Earth.
Right, because being volatile, they should be volatilizing. They should be gassing off all the time, but they're still around.
Yeah, especially the ones that are kind of deep in the Earth, that are kind of locked up in rocks and things like that. How did they get back in there, if you like?
Okay.
Because they should have been volatile off. That's
There's a
not
word for this, I'm sure.
Yeah.
I'm sure someone will
A nice
contact us
chemist
and
will
tell
tell
us.
us
Yes, yes.
what the word is. Yeah.
The word you're looking for is...
Yeah.
But no.
Okay, so that sounds a little bit puzzling, but
Okay.
maybe something you
Doesn't
could-
quite
you
fit.
could solve. But
We're missing something there.
right, let's come back to this idea then of the isotopes. Mm-hmm. Turns out they're too similar.
Too similar.
Too similar.
The answer's too good. The puzzle pieces fit too well.
Yeah, so in the case of the titanium, we're talking about exactly the same to 4 parts in a million.
That's pretty good, but I'm still struggling to figure out why that would be a problem. Surely that's a really big tick to say, yep, there's no question here, these came from the same place.
Well, the problem is if you think about what happened to Theia. So Earth would have had its own composition of different isotope ratios.
Yep.
Theia would have had should have had quite a different composition.
Yeah.
So if you smash those two together, you should get mixtures, right?
Yes, Earth and Theia, or Earth 1 and Theia would become Earth 2 and the Moon, and they shouldn't be that for like 4 decimal places similar. They
Yeah.
should be a mix and a bit sort of messed around.
So if you say the moon is kind of mostly made of the stuff that came off Theia, maybe with a bit of the Earth mixed in, then that doesn't really work.
No.
The
No,
only
I
way-
mean, unless there was a really, really, really good mixing that happened when that collision happened, which I wouldn't have thought there would have been a lot of time for that.
Yeah, and one of the problems, another problem actually with that is that there's absolutely no evidence that the whole Earth was ever all molten.
Right.
So we have old geological samples that suggest the Earth didn't become just a giant liquid blob, right? It may have had an impact that had changed certain parts of it, but probably not the whole thing.
So the fact that the Moon's isotopes of various different elements and the Earth's ratios of isotopes of various different elements are really, really, really similar is actually, in a strange way, evidence that we don't understand where this thing came from. How do you explain that?
Yeah,
Did the Earth just sort of burp up a moon? I mean, how does this? What happened?
So we started running models, of course, to try and understand, how the dynamics work. Where does the material go if you smash these two things together? And a 2007 study came out and said, well, basically, if you run all the models, there's like a less than 1% chance that you end up with the stuff that we have in the sky now and the ratios of isotopes, etc., that we have now.
And all of these models are, let's bash a planet against a planet and see what happens.
Yeah.
And less than 1% of the time you end up with what we've got. Which could happen, coincidences
yeah.
happen, but your gut would be saying, or...
You get a bit suspicious.
There
don't
may
you?
be another explanation.
Yeah, and if you add in all the other data, basically there's no self-consistent model that takes you all the way from initial impact to moon formed.
Damn it. Okay, that's embarrassing.
Yeah.
This thing that we really thought we'd nailed down and turns out not so much. Okay. So where do we go from there? Do we have to abandon that model entirely, or do we just need to tweak it a bit?
We don't have to abandon it entirely. And this is where I started going down the rabbit hole of really exciting stuff. Because some of the more recent research into this is suggesting maybe if we sort of add this other element to the whole system, then we can resolve some, if not all, of these problems.
So it's not that we have to throw it out entirely. It's that we were just missing a few pieces of this particular puzzle, which make it all work out.
Yeah. And so the idea to put this all together is basically that we have a kind of co-evolutionary model. So things form together. And I'm going to try and say this right because this is a new word to me, and this is very exciting. It's called synestia.
Okay.
I think that's a good way to say it. It sounds quite good anyway.
Anyway, let's go with that.
We'll go with that, synestia.
How do you spell it?
Synestia.
Synestia. That sounds right. Synestia. Yeah.
And
again, someone will contact us and say, actually, the way you pronounce that is...
So the way that this word is formed is basically the prefix comes from meaning together, and the suffix, if you like, comes from the word Hestia, which is a goddess, Greek goddess, who is kind of the Greek goddess of home and architecture and structure, that kind of thing.
So putting these two things together, then you've got your home structure being formed together.
Yeah, connected structure is the paraphrase.
Let me guess that this new word that you've uncovered has something to do with Earth and what's this other planet? Theia? Theia have a common origin? Is that what we're talking about?
Well, at least the Earth and the Moon have a common kind of origin in the structure that they have now.
Right.
Okay. So let's rewind. So we started off thinking, well, maybe there were some ideas in 2012 that maybe we need to have an impact, but then we need to have another impact to kind of mix things a bit better. And it started getting a bit messy.
It's starting to get very complicated here.
Yeah. So some researchers from lots of different places around, but I've seen some of the work published out of Harvard, for example, came in 2017, 2018 about the synestia. And you look at basically after impact, you end up with this weird donut shape around what is kind of a pre-earthy shape. And it's a weird shape because what is happening is there's a really interesting relationship between the angular momentum that's of these two objects that's going on.
So the angular momentum being the spinniness, the quantifying the rotation.
Yeah. So in physics, and especially in space, you have to conserve angular momentum, right? So if you take the example of ice skaters, which is kind of the very classic physics example.
It's in all the physics textbooks.
Of angular momentum. You've now got two bodies with two different angular momenta that you're putting together. So if you have two ice skaters, they come together, they link hands, then they can spin around and round and round each other, right? They're exchanging angular momentum. And this is a little bit about what this donut is all about. But in this case, it's not a donut that's rotating as if it were actually a donut. So what I mean by that is it's not a solid body.
Okay.
So if you think a donut, if you just spin a donut on a table, then, you know, the icing would spin at the same rate as the gooey donuts and sides.
You said I had tortured analogies. And I'm now getting really hungry because now I want a donut. But yeah, okay, I'm now imagining a donut which is solid, spinning around on the table in fairly random and analogous fashion. Yep.
Yeah.
So what now you're saying is not doing that.
It's not doing that. So imagine like the outer layers of the donut are spinning at a different rate to the inner layers of the donut.
So I'm now imagining a donut which is mixing itself around because different parts of it are spinning at different rates.
Yeah. And some of the outer bits of this donut reach a limit we call the co-rotation limit. And at this limit, basically the outer edges cannot spin any faster. And they effectively start orbiting what is the pre-Earth in the middle.
Okay.
So instead of being kind of a disk that's rotating, you've got kind of a spin that's meaning it's more like an orbit. And the physics starts to happen, and that makes this this type of object behave a little bit differently than it was just a spinning coalescing disk, which is what we had with Theia. basically you have, as you're cooling, droplets can form on the outer bit, which is a little bit cooler, and then sink towards the center. And that also changes the whole angular momentum distribution of the object. So you're changing where the mass is, which means you're changing the rates of spinning. Basically, and you rain the stuff inwards, then the moon starts to appear in the bits that you've left over after the rain, and the Earth very slowly forms afterwards.
Wow. That's far more complicated than anything we'd thought of previously.
Definitely.
No wonder we didn't stumble across that. So we've got donuts, but not solid donuts, whipping around. We've got some crazy physics of angular momentum going on there. Just go back over that. So which part of that was the moon?
So somewhere in the middle of the donut, the moon starts to form, basically.
Because of these crazy dynamics between sort of the outer and the inner and the different physics involved, you've then got the coalescing of bits and pieces in the middle of all of that to make the moon. And the rest went
into the Earth.
So they are coming from the same stuff.
Yes, exactly.
That's the point.
And the raining bits that go down into the center end up being some of your more volatile elements. So that's a partial explanation as to why the Earth has the volatile elements, but not the moon.
Blimey. I mean, that's really clever.
Very, very clever.
That's very clever. But it's not surprising that we didn't just trip over that explanation.
No, it's kind of...
it's quite complex.
It's a quirk, if you like, of three-dimensional rotational dynamics.
And who doesn't like a three-dimensional dynamics quirk? I mean, that's made my day.
And this probably didn't take very long to kind of happen. I mean, the estimates maybe say a few hundred years, if not less than 100 years.
Wow, really?
Yeah. So very, very fast.
On astronomical timescales, that's a blink of the eye.
And now we're thinking, well, this kind of event shouldn't be isolated in our solar system or indeed any other solar system that we have in our galaxy.
Yeah, because then you'd have to explain, like on the one hand, you've got, it's either that 1% or less than 1% of all those models from the original, planets colliding, do we get the moon, let's model it, less than 1% of the time we get what we see. So you've either got that, or you've got this weird donut thing that you just described, which is incredibly rare and we've never seen it anywhere else. And that's just as weird, surely, if not more weird. So do we see it elsewhere?
Well, we suspect actually it might be more common than it seems.
Because that's what you'd hope. If you go and see it somewhere else, you go, okay, this is a thing, not just some figment of a fevered imagination of an astronomer or an astrophysicist somewhere.
So we suspect that maybe more than half of all planets have something like this as part of their formation history.
So what's the evidence for that?
So it's modelling. It may not always result in a moon, or at least the singular large moon like we have. But if you have these kind of donut structures, then it seems to be linked to the actual formation of the planet itself. Wow. So yes, we need to go and find some more, of course, to back that up.
Part of the problem when you say go and look for more, I mean, if what you say is true, that it might have only taken a very short period of time for this to actually play itself out, for the donut thing to then go through its dynamics to say planet over here, moon over there. If that's relatively very short periods of time, we're talking maybe hundreds of years in astronomical timescales, that's nothing. You've got Buckley's chance of seeing that in action.
Well, indeed, this is where it gets really hard.
You're looking for secondary effects of that.
You're for a very transient event. Yeah, and the sample, if you like, of disks that are forming planets that we can see any detail in is also incredibly small.
Yeah. I mean, the principle that we often operate on this show, as in astronomy generally, is take very rare things and fill a universe full of stuff, and you'll spot some of them reasonably regularly. But this one seems to me like, but you're really even pushing the boundaries of that principle. You've got no chance of seeing that, have you?
No, well, not directly, probably, I think.
Okay.
So we have some examples of these young forming systems. We can see planets formed. We can see kind of warm blobs of material that appear to be kind of around planets. What shape they are is indistinguishable using our current technology. So we've got to think of some more secondary ways, like you said, in order to be able to determine these. And I haven't got as far in my reading as to figure out what is going to be the next thing. But
given that this stuff was only really done in the last maximum 18 months, I think you're forgiven for that.
Yeah, I mean, it's super exciting, though, isn't it? Yeah. So it kind of, for me, puts on a new perspective as to, for example, we've got 3 more missions that are supposed to land on the moon before the end of the year.
Right.
We've got the India's going to send a mission, and that's going to be a lander. We've got the US sending a privately operated, so non-NASA mission. I think that's one's called Moon Express, after Mars Express.
Yeah, fair enough.
Yeah, so, and that's going to be another lander. And China are also hoping to do a sample return mission before the end of the year. So you sort of think, well, there seems to be this huge resurgence in the moon's popularity over the last few years. And now I'm starting to really get a better impression of why. It's because we're starting to realize that actually the moon's origins might not be quite as simple as we thought they were. And that's quite exciting.
It is really interesting, isn't it? That, I mean, there is a certain degree of coincidence that it was 50 years ago, and 50 is a nice round number, and human beings get excited by anniversaries and stuff. But 50 years ago, humans stepped on the moon, and that's kind of cool. And so big celebrations about that this year. But it happens to also coincide with a huge, huge surge of private and government-funded space exploration. You know, after a few decades of, I think it's fair to say, not a lot of activity in the direction of the moon. Suddenly everyone seems to be going there, and there's a lot of companies from, you know, Elon Musk and Amazon and Virgin Galactic, everyone starting to pay attention to space, but then other governments as well who haven't been spacefaring governments before now going, nope, we're going to go there too. I mean, didn't Israel just crash something into the moon accidentally?
Yeah, they're going to have another crack as well.
Yeah. So, you know, the timing of that, where private space flight and space exploration and transport is really becoming a thing. It's a golden age. It's all happening. We might actually be able to solve this puzzle that up until a little while ago we thought was already solved. That's kind of cool.
Yeah, and what's great about it is soon we are actually going to be able to broadcast back from the moon because we're going to put 4G on the moon.
4G on the moon?
4G on the moon.
What?
So that we can have a live webcam.
Really?
That's all you need 4G for, right?
That's bonkers. Is that true? Why are we putting 4G on the moon?
Why would you not put...
Well,
I mean,
enough.
astronauts got to watch pictures of
That's
cat
right,
videos.
yes. Well, look, that escalated quickly. I wasn't expecting a discussion about the origins of the moon to become quite so complicated, but it is very, very cool. I love the fact that something that seemed so simple became much, much more complicated, but in a way which physicists and astrophysicists really love, which is, no, wait, look, check this out. Let me do some integrals for you. This is great. We can work this out. It's a donut, but trust me, it works. I love that. That's really cool.
Yeah, and you're going to have to add into the episode notes all the lovely links to the images of this because...
Oh, trust me, I'm all over that. It's going to be happening. Don't you worry.
Fantastic donuts. I mean, it is actually even a slightly weird-looking donut. I mean, if you went down and got a Krispy Kreme that was this shape, you'd be a bit psyched out by it.
Oh, look, I'm looking forward to seeing these. This sounds really good. But unfortunately, we are going to have to wrap it up there and leave the discussion of moons and donuts behind. And listen, there's one other really important thing that we need to tell you about. We've got a very special event coming your way soon. If you like podcasts and you like live audience participation, then have we got a treat for you. We'd like to announce the great Syzygy Space Off. We're going to do a live podcast recording here in the city of York in the United Kingdom on Thursday, the 23rd of May. Now listen, I know a lot of people in the world don't live in York, but if you do, or if you live in the surrounding area of York, you should get in on Thursday the 23rd, 7:30 p.m. at the Micklegate Social and come along and join the audience for the great Syzygy Space Off. Emily and I are going to have a little competition and the audience is going to choose the winner on the night. We're going to be throwing around our favourite space things in contest against one another for points and glory and victory on the evening. It's going to be a lot of fun. And it's brought to you by our wonderful patrons over at patreon.com. When we talk about supporting the show through Patreon, we talk about being able to do things that we ordinarily wouldn't be able to do. And this is a really good example of that. We're putting on this live show thanks to the support of everyone over at Patreon who supports the show. So thank you to everyone who allows us to do this. Come along and join the audience. It's going to be great fun, isn't it, Emily?
Yep, come along and vote for me.
No,
Just
vote
me.
for me. No, it's going to be really, really good. So get in and do that if you can. So listen, if you want to get in touch with us, there's a number of different ways that you can do that. You can go to our website, syzygy.fm, where you can find all of the past episodes, all of the show notes, all of the amazing pictures of donuts and other things. We're also on the Twitters, Emily.
We are at SyzygyPod, SYZYGYPOD. See, I can spell it all now.
Well done. Well done.
I'm doing well. I haven't met my challenge yet. I'm getting onto the Instagram next.
Come on, you were supposed to do that last week.
I know.
What are you
know.
doing? What are you doing?
I'm too busy looking at pictures of moon formation theories.
If you want to get in touch with us, you can do it through the website or through any of the above-mentioned social media. And send us a hello, send us a question, send us a comment. Tell us what you think about our social media capabilities. You never know. It might actually have an effect. And one last thing. Please, if you want to help us out, then give us a mention. Give us some stars. Give us a review on your podcast catcher or podcast network of choice. On Apple's podcasts, on Spotify, on Google Podcasts, whatever. Doesn't really matter where it is. What matters is that you do it, because that helps other people to find us. There's a lot of podcasts out there now in 2019, and we want to rise up through the noise and be heard around the world by astronomy nuts who might enjoy what we do.
We want to coalesce into a lovely big moon.
Preferably via the crazy donut stage. Anyway, that'll do it. We'll be back again in a week or so. So until then...
See you later.
Okay, bye-bye.
That crazy.
Oh, it is.
It's just physics.
Did you hear yourself? It's bonkers. It's totally bonkers.
Well, but it's classical mechanics.
Oh, yeah. I mean, it's good. Don't get me wrong. I love it. But compared to the nice, very simple, pithy, yeah, you know what, there was an impact and you got the moon. No, we're now actually having to do some integrals for this one. I mean, this one's really hard. So
Love me a good integral. That's all I
mean. No, don't get me wrong. I'm all over this. I think it's great. This theory incorporates the possibility that Earth... No, Siri, I didn't.
You're going at me about turning my phone off.
I put it on... Just for the record, my phone is on Do Not Disturb. I'm now going to put it on Shut Up mode. Siri, seriously. That's enough. It's enough from you.